This physics question is mostly about work energy and power as a cyclist goes up a hill. There are explanation parts as well as calculation parts. For part 1, figure 8 shows a cyclist going up a hill. The angle theta of the slope of the hill is constant. The total mass of the cyclist and the bicycle is 65 kilograms, so let's draw that on our diagram. So downward weight force, 65g, and then we want to write an expression for the component of the total weight parallel to the slope. Okay, so we want to get, if I draw a line like this, such that this is perpendicular to the slope, we want to work out this component over here at the bottom. So that's the component of the weight force that would be parallel to the slope. So we can do that by first of all knowing that this angle here would be theta, and if you're not sure why that would be theta, I'll explain a bit after I do this calculation. So that would be theta, and then this component over here, which is the opposite, that's the component that is parallel to the slope, that will end up being 65g sine theta, using SOHCAHTOA. So that would be our answer. Okay, so then if you're not sure as to how I got that angle, I'll draw another diagram that makes it a bit easier to understand. So here is a slope, here we have a particle, the angle to the horizontal, let's say, is theta, and then we have a weight force going down of mg. Okay, so then drawing another perpendicular line, and then here is the parallel. So this triangle is a right angle triangle, the one here that is. That means that this angle here, because all of the angles add up to make 180, this must be 90 minus theta. And then because this is a right angle, that means that the orange angle that we have here plus this angle must add up to make 90, which then makes this angle here theta. For part 2, the useful power output of the cyclist is 310. So useful PU, and then we're told the cyclist's speed as well as they go up the hill. So V is equal to 1.63. And then we're told air resistance is negligible, and we want to work out what theta is. Okay, so if there is no air resistance, then that means there are two forces that we need to consider for our cyclist. We have the driving force going up the slope, so let's call that Fd. And then we also have going back down the slope, this component of force that we worked out earlier, or we got an expression for earlier. Those two things should be equal. If the cyclist is going at a constant speed, and these are the two forces parallel to the plane, they should be equal. So let's write that down. So we know that the driving force would be equal to the component of weight going down the slope, which is 65g sine theta. And the useful power output, we can use the equation power is equal to force times velocity. The useful power output will then be the driving force, Fd, multiplied by the speed. And then we can rearrange this equation for theta. So let's write this out. So useful power is 310. Driving force is 65g sine theta, and then V is equal to 1.63. Rearrange, sine theta is 310 all over 65g times 1.63. This gives us 0.298, etc. Inverse sine of that, and we end up with 17.4 degrees. And for 7.3, figure 9 shows an alternative zigzag path taken by the cyclist up the same hill. She maintains a steady speed of 1.63 meters per second. Discuss how her useful power output when taking the path shown in figure 9 compares with her useful power output in question 7.2. Okay, so the first thing for this question is that when you take this kind of path, this zigzag path up a road or up a hill, the angle to the horizontal decreases. And that should make sense. If you imagine driving up a mountain or driving up a hill, you could just drive straight up and the angle to the horizontal for that road would be quite high. Or you can take a zigzag path up the side of the mountain and the angle to the horizontal on average would be much lower. Okay, so theta decreases, we know that. What does that do for the quantities that we're considering? So we want to look at how power changes. So let's start by thinking of what power equation we're going to be using. If we go back to the previous part, we have power is equal to driving force times speed. So we know that. Let's write that down. So the useful power is equal to the driving force multiplied by the speed. We know that the speed is constant. So let's write that down too. So V is constant. Now if theta decreases, then that would mean that the component of weight that is parallel to the slope, which was also what the driving force was equal to, remember that that was 65g sine theta. So this on the right hand side, if you remember, was the component of weight going down the slope. And we're not considering there to be any air resistance because we're still moving at that slow speed. So therefore the driving force will just simply be equal to that component of weight going down the slope or parallel to the slope. Theta goes down, so if theta goes down, that means that sine theta goes down as well. And if sine theta goes down, that would mean that the driving force goes down. And if the driving force goes down, looking at this equation that we have here, then the useful power output would also decrease. So useful power output is proportional to the driving force. The speed is just constant, so we're not considering that. Driving force goes down, and therefore useful power output goes down. Okay, so now we need to phrase this in a way that gets us 3 marks. So we can start by saying, with the path taken by the cyclist, the angle of the road to the horizontal decreases, and therefore the component of weight parallel to the slope decreases. As the cyclist is moving at the same speed, there is less useful work done by this force per second, and that reduces the useful power output. The cyclist reaches the top of the hill. She then travels back down the hill in a straight line. The bicycle rolls freely without the cyclist pushing the pedals or applying the brakes. Figure 10 shows the variation of her velocity with time as she goes down the hill. Okay, so there's no driving force. And we want to, in this question, determine the acceleration of the cyclist 10 seconds after she begins to go down the hill. So, to get the acceleration from this graph, we have a velocity time graph. We can work out the gradient at 10 seconds, and that will be our acceleration. So we can draw a tangent at this point, which would look something like that, and then we can work out the gradient of that line. So the gradient of that line, acceleration would be change in v over change in t, which is the gradient. The change in v, if I consider the end point and the start point, so the change in v would be 16 minus 10. So that would be, well, I'll write it as 16 minus 10, that would be 6. And then for the denominator, the time for the top point is 29 seconds, and this starts at 0. So 29 minus 0 would be just 29. And this would be 0.207. So that will be our answer. 0.21 meters per second squared. Okay, now for the final part, 7.5. Energy transfers occur as a cyclist travels down the hill. Outline how these energy transfers explain the shape of the graph in figure 10. Okay, so to begin with, there is no air resistance. That was what we were assuming in one of the previous questions, or some of the previous questions. Air resistance is negligible. So that will change as the cyclist speeds up. As speed increases, the drag force will increase with it. So then if there's no drag force to begin with, then all of the gravitational potential energy that is lost per second will be transferred to kinetic energy. And as our drag force increases, a greater share of that gravitational potential energy will be transferred to kinetic energy of the air molecules that the cyclist collides with. And eventually, when she reaches maximum speed, so this portion of the graph here, that would be when all of the gravitational potential energy is being transferred to kinetic energy of the air molecules per second. and none of it will be transferred to the kinetic energy of the cyclist.